This example demonstrates how to carry out less trivial combinations of tabulated loads. To this end, we consider a beam subjected to a zigzag load as shown, and our task is to compute the deflection at the center of the beam. This load is not included in the tables, and so what I pick from the tables are three possible loads to consider. Why these three? Well, each of them may be argued to be useful. There could be other choices, and you may try other possibilities, but I decided to pick these three, and this is absolutely kind of random choice, if you wish. Maybe not random, logical, but definitely other options are possible. So I will try to use these three to put something together. And to this end, I observe that the zigzag load can be thought as a subset of the linear load of intensity 2q0. So the red subdomain of the triangle is the zigzag load, and the blue part that looks like parallelogram, but in reality what it does, it represents a uniformly distributed load on the right half of the beam. So what it means, I can take a linearly distributed load of intensity 2q0, subtract from it a uniform load distributed on the right part of the beam, and that's what will give me the zigzag. So it turns out that from the previous slide where I suggested three tables, the first and the third table are important. The second table was not used. But let me also mention that the table on the previous page, the one in the book, has this load distributed on the left part of the beam. So what does it mean? It means I need to go from my superposition to this one. But this superposition is exactly the same as this one because I'm interested in the deflection in the middle. And it's clear that the deflection in the middle due to this load is equal to the deflection in the middle of this load, right? And that's an important observation here. And I'll take advantage of it. And so now I have a clear path toward the table. And let me see how it's done. So the desired case is the difference between a linearly distributed load of intensity 2q0 and a partially distributed uniform load of intensity q0. And now here is the table. So that's the displacement in the center. I evaluate it by replacing q0 here with 2q0 because I have 2q0 here. And then I have the second case. Here I rewrite everything as is. And now all I have to do is subtract from this deflection, and of course this gives me the final answer, 5 over 786 q0 L to the 4 over EI. Okay. So I want to suggests that there is an alternative solution. In this alternative solution, I take the original beam and I observe that if I flip the load, so my zigzag starts with Q naught on the left and ends with 0 on the right, then of course, if I add these to loading, I will obtain a uniformly loaded beam of intensity Q naught. Then I observe that the displacement at the center of this beam plus the displacement at the center of this beam is equal to the displacement at the center of this beam, and this is of course the tabulated beam, and their answer is 5/384. But then I also observe that the displacement at the center of this beam and this beam are equal. And since they're equal, they must be equal to half of this displacement. And that's what is stated here. And that's exactly the answer we obtained in the previous exercise. So the bottom line is, sometimes you have to be a little bit creative about combining the solutions.